Okay, excellent. So let's start with the second talk in the morning session in Europe. We have a pleasure of having Jose Barbon from the Institute for Theoretical Physics at UAM Madrid, who's going to tell us about the holographic complexity of matter infall. So Jose, please take it away and let's make this talk as interactive as the previous one.
Okay, thank you. Thank you very much to the organizers for inviting me, and especially I would like to congratulate them for putting together this amazing planetary event with all these time zones. It's pretty impressive. So thank you very much. Okay, so the title of my talk is Holographic Complexity of Matter Infall, and I would like to start by explaining what I mean by this. What's the basic concept of interest here? So, oops, there is some. Okay, so there is this slogan, which we are used to, that gravitational clamping increases complexity of the dual quantum state, assuming that you have a complete description which involves gravity via holography. Okay, so we know that there is a spectacular version of this which is at the root of the discussions of complexity, which is that if these three apples end up making a black hole, then after the black hole has settled down and nothing seems to happen, then complexity is still growing linearly because of something that is growing inside the black hole. But this should be also true even when you have three apples falling together before they form a black hole. Okay, and we know that this is physically, at the level of physical intuition, is true for standard definitions of complexity in the bulk, namely, say, volume complexity, action complexity. You just can take some spherical shell of dust or any spherical shell of material, thin shell, and you can compute volume complexity, or you can compute action complexity, and you find that when the shell is imploding, the complexity grows, and when the shell is outgoing, the complexity diminishes. So the figure of merit that controls the growth of complexity seems to be the momentum of some notion of infall momentum. So the notion of momentum going inward. Okay. So I will refer to this heuristically as the momentum complexity correspondence in a very generic way. Okay, which would hold sort of generally for matter distributions, and there should be some notion of infall momentum that is associated to the notion that complexity should grow, let's say. Okay, so that's the, if you like, the heuristic background, and the main idea of the talk is the following: is that if you look at complexity equals volume, which is what I'm going to talk about all the time in this talk, so I'm going to focus all the time in complexity equals volume, I will try to convince you that this prescription comes equipped from the factory already, comes equipped with a natural notion of momentum complexity correspondence. Okay, I will refer to this momentum complexity correspondence by PVC, P for momentum, VC for volume complexity. And it is natural because it seems to follow just from the momentum constraint of general relativity, with some caveats. Okay, so basically the idea is that you can use the momentum constraint of general relativity to give some mathematically precise formalization of this idea that matter infall increases complexity. Okay, so that's the main idea of the talk. This is based on work that will appear soon in collaboration with the real authors of the work, who are my students Javier Martín García and Martín Sasieta. You can see some preliminary ideas behind this in a preprint that we put out last December. And okay, so this is basically the idea of the talk. I should say that this notion of infall momentum related to complexity of quantum states actually goes back a long time to the beginnings of holography. I mean, if you read the papers by Lenny Susskind and collaborators in the early 90s, whenever you see these concepts, weak partons, string beats, everything that has to do with discretized light cone quantization of strings falling into horizons, it is an avatar of this kind of idea. okay? Because the longitudinal momentum, the light cone momentum of the string determines the number of partons in the description of the state of the string. So as the string, for example, falls into the black hole, because of this famous effect that freezes the motion of everything, including the oscillation of the string, more and more modes come into your scrutiny below your cutoff, your ultraviolet cutoff, and then as the string freezes on the horizon, you actually see more of the string. So the string grows and you get this kind of picture of the stretch horizon as a kind of a Hagedorn density of strings or something like that. So because this was a lot related originally to the notions of a stretch horizon or giving a structure to the stretch horizons, a lot of it was carried in the context of characterizing it in terms of entropic variables, entropic characterizations. But recently, it seems that quantum complexity is the right accurate concept to represent these notions. Okay? So for example, recently we have seen quite a lot of work in concrete models of fast scramblers in which you relate operator growth to radial momenta of infalling particles in purported dual descriptions in the bulk. The relation between the operator and the particle is that the operator is supposed to create the particle on the boundary and the particle goes in. And then you can write equations like this, where the size of the operator, the rate of growth of the size of the operator is related to some radial momentum in the bulk. Okay? This could be, for example, in some SYK model. And a lot of work has been going on recently on these matters. If you consider the particle near the horizon of a black hole, then there is a nice universal behavior for the Rindler radial momentum, which grows exponentially with a Lyapunov exponent, which is the same Lyapunov exponent that you can read off from OT-OC correlators in the dual description. So this is very nice. And this is a picture that works nice up to the scrambling time, which is when the operator basically grows to the size of the system. But beyond the scrambling time, at long times, you expect that complexity keeps growing, the complexity of the operator, which is now not well represented by the size of the operator, because the size saturates, but the complexity of the operator should keep growing linearly, because it should reflect basically just the complexity of the time evolution operator at long times. This is even true of other definitions of complexity that have been proposed, other notions of operator complexity, like, for example, K complexity or Krylov complexity, which is roughly the number of nested commutators with Hamiltonian that you need to approximate the Heisenberg operator after time t. In this paper here, we have shown that we have gained arguments that show that if you assume, you make standard assumptions about the operator, namely satisfying the Eigenstein thermalization hypothesis, the statistics of eigenvalues is the one that you expect for chaotic systems, then you find that K complexity grows linearly at long times. Okay? So this is kind of a natural thing to imagine that there could be a momentum complexity correspondence for operators at a very long time, and should be compatible with the fact that complexity of operators would grow linearly in time, okay, at a very long time. But if that is true, if there is such a momentum complexity correspondence, at long time, linear behavior for CO means that P has to sort of freeze, has to become constant. Then there is this kind of funny thing, because if you are thinking of a particle, at very long times, the particle, you should be describing it inside the black hole, probably. So what can be a frozen momentum inside the black hole? Because inside the black hole, nothing is static, and the particle just goes to the singularity, which is an ultraviolet place. So momentum blows up. Any mechanical momentum will blow up there. So how can this be compatible? One possible idea is that the correct time slicing in which this relation holds saturates inside the black hole. Okay, so that the time slicing for which this is true, an equation like this is true, has this property of saturation inside the black hole. And then we have seen this before. This is just the behavior of extremal surfaces for volume complexity. Okay, if you take the extremal surfaces of volume complexity as your time slicing, then it will have this property, right? So this is suggesting that if you define the operator complexity in terms of some quantity that you can represent using volume complexity, you will have more or less, or granted probably, PVC relation of this kind that will be consistent with linear behavior at long times. So with this in mind, we examined a very simple situation in this December paper. We studied a volume complexity analog of all this by just defining a notion of operator complexity, which is just you take the thermofield double, you perturb it by an operator which creates a shell, a thin shell that goes in, and then you subtract the complexity of this system from the complexity of the bare thermofield double. So it's like computing the complexity of the perturbation, right? The relative complexity between the two situations. Okay, so this is a definition which is different from the previous ones I mentioned before, but it's interesting to check if this definition has a natural momentum complexity correspondence. Okay, so we did that, and we found that you can write it. There is one, and you can write it in a very suggestive way. It turns out that you can write it like this, as an integral of the flux of momentum through the extremal surfaces, weighted with a vector field C, which I will call the infall vector field, which tells you basically what type of momentum you are counting. Are you counting radial momentum? Are you counting sideways momentum? Are you counting angular momentum? Okay? So this C field projects the density of momentum in the direction that is relevant for computing the complexity growth. Okay? So this formula that I write like this is just the result of reverse engineering from just the calculation of the thin shells, right? And I should say that, well, first of all, let me just tell you what is the concrete form of C that we found for thin shells of dust that we considered in our paper. So in that case, the extremal surface, you can just make an ansatz for it, for the induced metric, which is spherically symmetric. And then the C field that works for that formula is one which is radial, is inward pointing, and its modulus is given by the radius, by the size of the angular sphere. Okay? If you use this field to define a preferred radial coordinate, which would be like the canonical dual to your momentum, the momentum you're picking, this preferred radial coordinate over the extremal surface will be the solution of this differential equation. So everything is determined, okay? And then you have this nice formula. I should mention that this notion of PVC relations is not new. I mean, the literature on thin shells is large, and you can find PVC relations like this. The fact that volume complexity rate is related to some momentum, some canonical momentum in many places. I'm sure there are more. The logic of this is that when you have thin shells, which are spherical, you can integrate out the angles, and then you have some effective particle, some effective 1 + 1 dimensional Lagrange. And then you have some radial coordinate, and you will have a conjugate momentum to the radial coordinate. And it happens that the rate of complexity growth is associated with this momentum. Okay? Now, the details depend a little bit of what coordinate you use. Do you use Kruskal? Do you use Ringler? Do you use Eintón-Finkelstein? And also, what type of shell do you use? Are the shells massive dust? Are the shells null dust? Are they branes with tension and charge? Do they have some internal equation of state with some pressure? So the details that depend a little bit of the logic is always the same. Okay? And from that point of view, our expression, the expression that we wrote down, the characteristic, the special thing about it is that we use the extremal surfaces themselves as the time slicing. So this is the main important choice. Right? We don't use Eintón-Finkelstein, we use that, the time slices themselves as a time foliation. This doesn't cover the whole space-time, but it covers enough to compute the rate of complexity growth by definition. And then there is this C field which selects some radial coordinate on the time slice, on the extremal surface. Okay? But what is interesting about this equation is that as it looks, when you look at it, it looks like it could generalize completely much beyond thin shells, because everything that depends on the dynamics of the shells is encapsulated in T mu nu. And now this could be a general T mu nu. I mean, it doesn't matter what type of shell do you have here. And everything else inside, it depends only on the extremal surfaces, okay? And this notion of infall vector field. So the idea of the paper is to, the idea of the talk is to try to see if this equation generalizes and how much, okay? So how much such an equation could be sort of hardwired into the complexity wall volume correspondence, right? So in order to do that, I'm going to work with asymptotically ADS space with unit radius of curvature. I will consider normalizable states characterized by some T mu nu in the bulk. So this T mu nu here is not the operator in the CFT, it's just the energy momentum tensor of bulk fields, the thing that enters Einstein equations. So I will assume Einstein equations in the bulk. And the extremal surface is anchored at point T. The complexity wall volume complexity is just the volume, some regularized volume of this thing with a normalization that I choose like this for no good reason. Okay. So this is the setup. And just for notation, the induced metric on the extremal surface I will call HIB. Latin indices are just indices with 4 coordinates on the surface. X mu are the embedding fields that put this surface in the target space. The unit normal is called N, and the tangent frame basis is these Firbeins here, right? Now, since sigma is extremal, is maximal volume, a first order variation of the volume itself is a boundary term, okay? Because the bulk term is just the equation of motion that tells you that it is extremal. So the first order variation will be just some integral on the boundary of sigma, which gives me, which depends on the variation of the embedding fields on the boundary pulled back onto the sigma, multiplied by these Firbeins, okay? Now, because I'm after an equation for the rate of complexity growth, I'm going to take a boundary variation, which is just a rigid translation in delta t. So it's a translation proportional to the asymptotic killing vector, right? The time translation vector, which in general is asymptotically killing in these space-times. And then by dividing by delta t, I get an equation for C dot, which is just given by the integral over the boundary of this pullback on the surface of the time translation vector. So to see what is this thing here computes basically the, I'm integrating over the boundary the scalar product of the time translation vector and the tangent radial vector that tells me how the surface is bending. You know? If there was nothing here, if there was just vacuum, the surface would be horizontal. So C dot would be 0, right? But because there is bending, although it enters orthogonally, asymptotically, because I'm integrating on a sphere that is growing, like r to the d minus 1, I have to pick the term in this scalar product that goes like 1 over rd minus 1, which is the leading term actually. So in this way, I get a completely cutoff independent description of C dot by evaluating the asymptotic bending of the surface because of the presence of this stuff here. Okay? So this is a very nice representation of C dot. Now, an obvious remark is that if I have any current, any vector field defined on sigma, which has the boundary condition that is equal to the pullback of the time translation vector near the boundary, right? So it has the same integral. Then I can compute C dot, I can rewrite C dot as using Stokes' theorem as an integral over sigma, assuming there are no singularities in any place, an integral over sigma of the source for this current, okay? And then this is just an identity. So the crux of the matter is to assure that this J has the right boundary condition. And then the idea is to use clever choices of J so that I can make here appear the momentum density, okay? So this would be a strategy to prove a generalized momentum complexity correspondence. Now, in the case of the spherical shells that we did explicitly, right, in the hard way, you can use this trick to just obtain the result very easy, very, very fast, right? Because now the obvious choice for J is the time translation vector itself, which happens to be a Killing vector everywhere in space-time except at the world volume of the branes, where it jumps, okay? So if I just declare that J is this, which satisfies obviously the boundary condition, when I compute the gradient, this gradient is just a bunch of delta functions on the intersections between the world volume of the shells and the extrema surface. And the jumps in the the jumps in the Killing vector just give me the coefficients of these delta functions, and these jumps are controlled by the Israel Judson conditions, therefore are controlled by the energy momentum properties of the shell. Okay, so that's a very easy calculation to do. You evaluate this by localizing the integral over the intersections, and you get an expression like this. You get a sum with a minus sign, intersections, the momentum in the radial direction upward, with a minus sign means that it's going to be downward. And then it is decorated by these factors Ri, which are just the sizes of the shells as they cross. So this is the size of the angular sphere here. Okay? And on the other hand, the energy momentum tensor itself of the shells is a delta function of the world volume, right? So I can just integrate also, evaluate this integral, right, over the whole shell or the whole extrema surface, and it's also localized on the same places, right? If I now make an ad hoc choice for C, so that to make appear these factors of Ri, the right choice is this one, then I get this relation that I advertised before. So this is, if you like, the fast derivation of this relation based on this trick of using this effective sort of Komar integral kind of argument. Okay, so this is nice, but then the question is there a clever choice of J that works more generally? Okay, as the form of the equation suggests, that there should be more general setup. Okay, after all, if I give you some spherically symmetric matter distribution, you could imagine that to some extent you could approximate it by a lot of spherical shells, sort of one after the other. Okay, like when you approximate a smooth function by some histogram, right? Of course, you are not guaranteed that the most general energy momentum tensor can be controlled in this way, but this suggests that the formula should have a wider degree of generality. So the answer is that you can almost do it, okay? And it will be interesting to talk about the almost. Okay, so now I will work backwards in order to get this, because I know that I want some integral of the momentum density over C, okay? And then the question is, where do I find a completely general equation that involves the momentum density over a space-like surface? And the answer is obvious. It's the momentum constraint of general relativity. Okay. So in case there are people here from quantum information that are not so familiar with general relativity, the momentum constraint is just some analog of like the Gauss law in electrodynamics. It's a constraint in the P's and Q's. It's a constraint in the positions and velocities rather than a dynamical equation, and is the result of the theory having gauge symmetries. So in general relativity, out of the 10 equations, out of the 10 Einstein equations, there are 4 constraints. There is the Hamiltonian constraint, and there is the other 3, which are the momentum constraint. And these are the ones I will talk about today. So if you have any submanifold, any space-like submanifold sigma, you have the induced metric on it, and you have the extrinsic curvature. The extrinsic curvature is like the time derivative of the metric, so it's like the velocity variable, right? Let the trace of the extrinsic metric be k. Then the momentum constraint, which is just 3 of the Einstein equations, looks like this. Okay, I can write it in this way. Here you see the momentum density. This is the momentum density over, this is the flux of momentum that crosses sigma, and then I just project it with the Firbein. I project it over the tangent plane to sigma, so I'm computing the momentum directed along sigma. Okay, this is a vector field, and this is just covariant derivatives in the induced metric. And then because sigma in my case is extremal, is a maximal volume surface, K is 0. And that simplifies the momentum constraint appropriately. Okay, so I get a simple equation. And then the idea is that I should integrate this equation, right? But because it's a vector equation, I need some vector field to integrate it. I need to multiply it, contract this index with a vector field. Let me call it C, okay? So I multiply by some vector field C both sides and integrate, right? Then when I integrate, I can integrate by parts this derivative here, getting two terms. And then the momentum constraint can be written in this integral form, okay? So given the C field, which so far is completely arbitrary, I have something that I will call the C momentum, which is just the integral of the momentum density against this C field. This C field could be whatever. It could be something that tells me that I am counting the radial momentum, I'm counting the outgoing momentum, I'm counting angular momentum, I'm doing a mixture of things, right? So far, this is a completely general thing. So I get a boundary term, and then I get a reminder term from the covariant derivative hitting C, right? After I change the order of the covariant derivative. Now, because this is a boundary term, the natural thing is to make this appear as C dot. So you want this to be C dot, okay? So that you get C dot equal P plus something that you have to negotiate later. So that's the logic of the argument. So the natural attempt is to define J, this finite current, to be this combination here, and adjust C, the boundary condition at infinity, so that J has the right boundary condition to compute C dot, okay? So the idea then is to find out what are the conditions on C. And for that, I need sort of invert this extrinsic curvature. So I need to calculate it. And for that, I will make a further assumption, okay, which is kind of a technical assumption. The assumption will be that I will assume ADM-like or no radiation conditions near the boundary. Okay? So what this means is that both for the spacetime metric and the induced metric, I will assume that the deviation from spherical symmetry comes in higher multipolar corrections that are suppressed by powers of 1 over r. Okay? So I'm not saying that I have a spherical symmetry, I'm just saying that the spherical terms that violate the spherical symmetry are subleading in 1 over r. Okay, like
sorry, but
the dipole term, the quadruple term, etc.
So a question. So shall I understand it as a condition on the metric in which your quantum field theory lives in?
Yes. It's a condition on the state. Okay, so I have this ansatz asymptotically.
Sorry, it's not a condition on the state. It's a condition on the metric. So the external source in which you put your field theory.
I mean a state. By state, I mean the gravitational state in the bulk. So that's the metric, the matter fields, whatever. Okay. I call a state anything that describes how the bulk differs from vacuum areas.
Yeah. Okay.
Right. So I get this spherically symmetric ansatz of that approaching the boundary plus subleading terms, and this is spherically symmetric ansatz also for the embedding surface. So what I'm excluding with this condition, what I'm losing somehow? What I'm excluding is this situation where I have a gravity wave that hits and reflects on the boundary precisely at the same time at which I'm hitting it with the streamer surface. Okay, this is the thing I'm excluding, and this is not really a very generic thing because, for example, this thing is allowed. Right? If I have gravity waves, I'm not banning gravity waves. I'm just saying that I don't want the gravity waves to precisely reach the boundary at the same time at which I'm computing C dot. Okay, so this is allowed, this is excluded, and this is a technical restriction. In fact, everything I say applies equally well to asymptotically flat volume complexity. And we don't talk much about that because we don't know what it means, but all the formulation works perfectly nice for asymptotically flat extremal surfaces. And in that case, this issue is not even an issue because gravity waves or massless fields go to different infinity than the space-like surfaces. So in that case, it is always true that if you go along this line, every violation of spherical symmetry will show up in higher multiples. Okay, and this is the technical assumption I'm making. I'm making it because I want to calculate KAB, and I want some ansatz which is manageable. Okay, so under that assumption, you find that the asymptotic boundary condition for C in order for C dot to appear in the game is this one. I have to make it approach infinity in this way. And these functions, both for asymptotically flat spacetimes and for ADS, they cancel out asymptotically. They are the same function. And therefore, you get the result that we got empirically for thin shells. This time, it's only asymptotic. So this is just an asymptotic boundary condition at infinity. Okay. So this essentially explains what is the origin of this infall field. It is just the right object that you have to put in the integral over the momentum density so that the momentum constraint, when integrated, contains C dot. Okay, so that you get an equation for C dot. So that's the logic of this thing. Now, so we have now a sort of a generalized PVC relation. Okay, we just integrated the momentum constraint. I got this right under these assumptions. This is C dot is equal to some momentum, which is just this integral of the flux of momentum against this infall C field. I only determine the form of the C field asymptotically. It's inward pointing, is radial, and it has a precise modulus. And then there is a reminder, which I forgot along the way. The reminder is just the covariant derivative hitting the C field, right? And in general, we have this reminder, right? So this generalized formula just tells me that part of the C dot, depending on the choice of C, will be interpretable as a momentum, and another part will be lingering there. Okay, so now the question is, what can we say about the reminder? Can we say that in some situation is zero? Can we say that this is small? What can you say? What can you say about the reminder in general? Okay, so the question is, all right, we have fixed the form of C asymptotically, but we can still choose C in the bulk, right? So can we get rid of the reminder by a clever choice of C, right? And here there is something which is very easy to notice, is that the reminder, because K is symmetric and traceless, because sigma is extremal, I can just write this as K times the conformal Lie derivative of the metric. Conformal Lie derivative is just the normal Lie derivative subtracted the trace. And I can do that just precisely because of the properties of K. Okay? But now this is interesting because the conformal Lie derivative vanishes precisely if C is a conformal Killing vector. Okay? So if the extremal surface happens to have a radial conformal Killing vector, it's a Killing vector, it's a conformal Killing vector and has this asymptotic behavior at infinity, then I can just kill the reminder and I have a pure momentum complexity correspondence. Okay? C dot equals some momentum, some appropriate momentum integrated over the extremal surfaces. All right. So when is that happening? I mean, what are sufficient conditions for that? Well, in particular, that sigma is conformally flat or conformal to a Poincare ball. Right? In that case, I can always find that C field. And this includes every possible solution of Einstein equations into plus one dimension. So, because in that case, the sigma is two-dimensional, and therefore, if it is the topology of a disk, I know that it's conformally flat. Okay, so in 2 plus 1 dimensions, every possible CV calculation which uses Einstein equations under these assumptions that I made will have a momentum complexity correspondence interpretation, right? Totally general. The other case is any spherically symmetric state in arbitrary dimensions for any energy momentum tension. Okay, so this intuition that you could approximate any matter distribution by thin shells somehow comes to pass. Any spherically symmetric matter distribution will have a sigma, which is spherically symmetric, and therefore it will be conformal to a d-1 dimensional Poincare ball. So I can always find the C field with the right properties, which is a conformal Killing vector, right? So this is nice because I don't need any energy conditions at all on T mu nu, right? This is totally general, it's kind of kinematical. And the reason it's kinematical is because it comes from the momentum constraint, right? So it's kind of interesting. Right. So these are the cases where you can get rid of the remainder term. In those cases, you can always find C, right, by a conformal transformation. So for example, if you take the Poincaré ball, C is this very nice infalling field, which is very symmetric, right? The modulus is just the radius of the sphere, and it's orthogonal to angular spheres. After a conformal transformation, this is some potato, and the C field is still orthogonal to the potatoes, right? And the modulus is given by the conformal scale, right? So this is the mathematical embodiment of that formalizes the cartoon of the apples. Okay? So if you want to give a precise meaning to when a distribution of apples or matter is going to have some C dot, which is positive or negative, what you have to do is to foliate your space by a nested set of potatoes, right? And if you can find a conformal Killing vector that is orthogonal to this set of potatoes, then you will have a relation that says that C dot is controlled by the effective momentum controlled by this vector field. Okay? If it is positive, then C dot will be positive. If it is negative, C dot will be negative. Okay? Now, to end, I should say, when is the remainder non-trivial? I mean, when you cannot get rid of the remainder, right? You cannot get rid of the remainder in general whenever you have gravity waves, okay? When you have gravity waves in the bulk, then the space-time will have a Weil tensor, so there is no reason, I mean, the space-time itself will not be conformal to anything very symmetric. So there is no reason why extremal surfaces on it will be conformally flat. In general, you don't expect, I mean, you could have particular times, particular configurations in which sigma happens to be conformally flat, but this will not be generic. We know, for example, that we can form a black hole by colliding gravitational waves. So there is no T mu nu from the beginning, there is no matter, energy momentum tensor, and yet after you form the black hole, complexity should grow linearly. So the buildup of complexity has to be accounted for by something that doesn't involve, right? So you know that when you have gravity waves, you should have some generalization, and then basically the remainder term should come in. What could be true is that although there is no general notion of local energy momentum for gravity, which could play the role of T mu nu, right, for gravity waves, you know that in perturbation theory you can have proxies for that. If you work with some background metric and you see the gravity waves as spin-2 fields that are just propagating there. So there should be some linearized gravity approximation to this equation that involves adding the T mu nu of matter and the pseudo tensor for gravity waves, lambda Lifshitz or whatever your choice, right? There should be such a formula. We are kind of working on trying to understand how this formula would come about, okay? But it will be approximate, right? Now, I put the question again because there is another situation which is amusing, in which the remainder term is also needed, okay? And this is that you can have topological abstractions. So, and the simplest one is just the simplest possible non-trivial topological situation, which is the wormhole of the thermofield level, okay? So here you have a beautiful extremal surface, which is cylindrical. You can have a very simple situation where it is spherically symmetric. So there is a conformal Killing vector, right? A radial conformal Killing vector, which is infalling, say, on this side. But the problem is that the solution of the conformal Killing equation is a vector that becomes outfalling in the left side. So if you use this conformal Killing vector, it measures infall on the right and outfall on the left. Okay? So there is a PVC relation. If you take vacuum, for example, T mu nu equals 0 here, there is a PV relation which says that dc dt equals P, and if P is 0, then this is 0, right? But of course, this T means the t which is dual to the Hamiltonian, which is h right minus h left. So it's the Hamiltonian for which time goes backwards on the left side, right? The reason for this is, of course, that the C field is analytically continued to the other side by solving the conformal Killing equation. And its relation with the Killing vector, asymptotic Killing vector, which is itself a solution of a Killing equation, okay, and is also transported to the other side, is maintained provided you use the analytic continuation for both of them. But you know that the Killing vector on the right side, if you just analytically continue to the other side, it comes backwards in time. So the object that has the nice equation of PVC form in the case of the wormhole is the complexity rate with respect to this Hamiltonian, not with respect to the standard both forward Hamiltonian, okay? So in vacuum, for example, you get C dot, or if you have shells or matter that comes in a Z2 symmetric fashion, so maintaining the left-right symmetry, you always will have C dot equal 0. This is because here you have infalling, so it will count positive, let's say, but here infalling counts negative because the C field here is outgoing. So what is counted positive in the left side is the outgoing material, okay? So with respect to this time variable, this situation will be stationary. And in order to get a non-zero C, you will need to have something which is infalling on the right and outfalling in the left, something like that, for example. Okay. Now, what happens if I want to compute the complexity rate for the standard Hamiltonian, right? Well, for that, the problem is that I need to define infall conditions independently of each boundary. I can do that, okay? There is a conformal Killing vector here that looks like this. There is another there that looks like that, but they are not compatible with each other. So I cannot maintain the conformal Killing equation everywhere. I have to somehow flip the field in the middle by hand, okay? So if I flip it smoothly, I will get a contribution from the remainder term from the flipping region. If I flip it suddenly, I will get a contribution from the sphere where I am doing the flipping. It will be a delta function contribution, okay? So for example, if you just do that, you flip it suddenly in the middle, right? Like a Heaviside theta function, then the gradient of C will get a delta function, and then when you compute this, it will be very easy to compute, and you can do it explicitly for the vacuum solution. You can compute this on the delta function support, and you get the standard result. Okay? So this is a very nice example which shows the importance of this notion of infall. Okay? So this physical notion of the C field representing the concept of something clamping, something infalling, is very important, and whenever there is conflicts, you have to face them, right? By, for example, computing explicitly these corrections. Okay, so that's it for the talk. I will end with some conclusions and questions now. So I hope I convince you that complexity equals volume has a very nice built-in sort of kinematical momentum complexity correspondence. It's natural and kinematical because just stems from the momentum constraint. And in particular, it doesn't depend on any conditions. You don't need to assume positivity of nothing. You know, it's very kinematical. And it formalizes this kind of slogan that I started with the apples, that there is a sort of connection between complexity and infall. We knew that this thing exists, okay, because we just computed with, from the beginning of the subject, we did examples, people did examples with thin shells, and you could see that this happens. But the question is whether this is kind of ingrained in the mathematics. And we found that it is almost completely ingrained in the mathematics with some caveats, like topological obstructions when the wormholes are present, because the notions of infall are conflicting. Okay? So you have to negotiate that. The main open question is what to do with gravity waves. You know, gravity waves remain elusive because you cannot relate them to a momentum. In a sense, this is natural because we know there is no local notion of momentum for gravity itself. So there is no candidate to integrate over the extrema surface. Right? And the question is there some nice generalization of these ideas which allows you to put a little bit more structure into the remainder term. Okay. Another interesting question is, what is the relation with the so-called first and second principles of complexity? This equation for C dot, which depends on the bending, is very nice. It's independent of cutoff or anything like that. So it could be, I mean, this kind of relations that relate C dot to integrals over T mu nu could be useful in reformulating or in deriving general properties of this kind. And then I could end just with the usual question about ACBC, or the general story that there are various candidate proposals for bulk or geometric measures of complexity. And there are all these questions about whether they are heuristically similar or technically similar or not. They differ in some respects, etc. What is the nature of their difference, etc. So here, for example, this is an example of something which is extremely tied to the machinery of volume complexity, right? So it's an interesting question. If you just take action complexity, for example, is there a natural momentum action complexity correspondence, and what are the ingredients? What are the mathematical objects that you are going to use to formulate it? Okay. So I think that's all. Thank you very much.
Okay, thanks, Jose. Let's unmute and applaud. We're doing well with time, so we have actually plenty of time for the questions. I already see the first one on the chat. It's from Eric Kramer. Could you comment on whether such a construction could potentially be extended to an evaporating black hole? That's the question.
Yeah, I guess so. I mean, this construction is completely classical. So you can imagine, for example, that if you consider some effective field theory description of the evaporation in which you compute the back reaction order by order in some parameter, like the loop expansion parameter for gravity or something like that, then you will have some, so that the black hole will be evaporating, so the geometry will be evolving not just because of Einstein equations, but because of the corrections to Einstein equations due to the fact that you're expelling material. So if you write down such equation, you can always ask what happens, and you should find that the growth of complexity is not exactly linear, but is tamed by the time dependence of the mass. In fact, there is a calculation, a numerical calculation by the group of Larus Torlasius in Iceland, where they do exactly that for dilaton black holes. So you can see how the back reaction affects the C dot. Now, whether you can write that in terms of some effective PVC again, some effective momentum, maybe, just the ingredients are there because you have some effective geometry which is evolving, and you can throw streamer surfaces on it, and you can try to define the. In that case, you would also have a flux of momentum coming from the energy momentum tensor of the Hawking radiation. So, yeah, it's an interesting question which will be technically involved probably to do, but I don't see any reason why it shouldn't be applicable.
Any other questions from the audience?
I actually would have a question. I'm not sure. Hi, so my impression is that here you're somehow assuming, from the field theory point of view, you're assuming that your excitation are delocalized, and so they would spread, and that's related to the increase of complexity. Is it correct that you're basically assuming that?
Well, not really. I'm not talking about the field theory, if you like, about the quantum system, the boundary description. I just did that at the beginning for motivation, when I talked about a little bit about these operator growth stories. In general, spread is related to going deep in the bulk, right? So the wave function of the states gets spread when you, in the dual picture, the things go deep in the bulk. And this has to do more with the radial momentum rather than the position in the bulk, right? So you have a particle that is going down, but it's going down after having gone up for a while and then stopping and then going back, right? The quantity that we are computing is related to the momentum of the particle, which vanishes at the high point, at the turning point. Right? So in that case, C dot would vanish. It doesn't matter how high it is. So the state could be very spread already because the turning point is occurring very deep inside. Right? So the concept is more like a bulk radial momentum, and this is a technical elaboration in which I'm trying to put some formal mathematical machinery on it so that I can see how general it is. Okay, but I'm assuming from the beginning the ansatz of volume complexity. So I'm taking critically the idea that volume complexity is computing something for the quantum field theory via the tensor network analogy or whatever. But yeah, the idea is more characterizing inward momentum than spread. Right? The story about the size of the operators has to do with the fact that in fast scramblers, the operators grow so fast that complexity is the same as size, more or less. Okay, so in that case, the size of the operator is a proxy for the complexity, and in that case, you are really the rate of increasing of complexity is the same as the rate of increasing of size. Right? But this doesn't happen if you don't have, in general, if you don't have a fast scrambler, and it doesn't happen in at very long times when the size is not growing anymore, because the operator has just grown to the size of the system and then cannot grow more.
Okay, thanks.
So I see two questions from Cyanton. The first question is it possible to extend the calculation in the Lorentzian signature, and can anyone give the generation of Lorentzian wormhole construction out of the present description?
Oh, everything was Lorentzian in my description. I was using Einstein equations. Time was real time. It's just that all the time you work with space-like surfaces because these are the surfaces that you use to compute the complexity. But everything was Lorentzian in the description, really. Nothing was Euclidean here. The wormhole the wormhole that I was drawing, this wormhole, for example, this is a fixed time picture, right? So this is the wormhole at t equals 0, let's say, inside the thermofield double or inside the eternal black hole. So it's a special section, okay? That's why it's just a special surface, but everything is Lorentzian here.
Any further questions on record to this talk? Well, maybe I have a last question. So I understand that your construction is very much tied to CV or VC. But do you have something to say about the other proposal?
I don't know. I guess there should be a version, but I just don't know how to make it because action complexity is a little bit like volume complexity when you become democratic about the Cauchy surfaces. You're not saying that you're committing to the extremal one, but you somehow look for something that accounts for the whole Wheeler-DeWitt patch, which is just the locus of all the possible Cauchy surfaces. So maybe there is some quantity that you can compute, which has some interpretation of some average momentum in some way. I don't know. I just don't know. You see that the way we worked here was reverse engineering the formula. Okay? We just found the formula and we said, oh, this formula looks like it will be very general, because of the structure of the formula. And then we just reverse engineered it. So it's hard to see how that would work in AC. I just don't know, but I think it's an interesting problem.
Okay, so I suggest we thank the speaker again and stop the recording afterwards. Thank you.
Yes, Michal,